Okay, good morning again. This is the Nominal Unification, the second section. I hope you enjoy the coffee. Then the first talk will be given by Daniele Nantes-Sobrinho from the Universidade de Brasília, and it's entitled Nominal Disunification via Fixed Point Constraints. Please, Daniele.
Hello, everyone. Good morning from Brazil. As Mauricio said, I'm going to talk about nominal disunification via fixed point constraints. This is a joint work between my students, Leonardo, Batista, my previous student, Deivid, Vale, and a collaborator, Maribel, Fernandez. I'm going to be the one presenting it. So this is the outline of my presentation. I start with some motivation, go to syntax, and then I give a brief review of nominal unification via fixed point constraints before I move to the disunification, which is the actual work, and then I move to conclusion and feature work. Okay, so the motivation, so this is an ongoing work. So the motivation is more technical. The idea is to extend previous results that we had about nominal disunification, like the standard presentation using freshness. So we are interested in solving like this problem, which consists of solving equations between nominal terms and also solving these equations. So if, just to give an illustration, if you have like this signature with a binary predicate P, a function symbol with a unary function symbol F, and for all n exists, that we are going to take them as function symbols. This equation between two first order formulas expressed in nominal syntax. For all x, P of x, Z is equal to, for all y, P of y, F of y, F of w, and we have this equation which says f of x that is different from f of. So a solution for this would be z go to f of w. So we are a method or a procedure to solve this problem. Okay, so basically we are going to present, we start presenting an axiomatization of alpha equivalence relation for nominal terms based on a primitive notion of fixed point constraints. We are in the session of nominal techniques, so it's like well known that fixed point equivalence in the nominal syntax is implemented using freshness. So for instance, A is fresh for X, means that if A occurs in an instance of X, it has to occur under an abstraction, so A cannot be free. So there's a way of implementing alpha equivalence using this predicate, but we follow another approach, like a more primitive one that was given by Pitts, which says that A is fresh for X corresponds to this equality, this fixed point constraint on the right, which says for a new name A prime, A prime of X is equal to X. So instead of using the freshness predicate, to use this fixed point equation on the right. And we are going to define and specify everything in terms of this more primitive notion. So why do we want to do it like this? Is because it's more convenient when we have equational theories. Specifically, if we have commutativity in our equational theory. So for instance, if you have like this fixed point equation, AB fixes X is equal to X, we want to find instance of X for which AB fixes this instance. And we have commutativity, so this alpha equality here is modulo commutativity. If you map X to A plus B, for instance, we are going to have X is going to be A plus B, so this permutation AB acting on A plus B is going to be alpha equivalent modulo renaming of bound variables to B plus A. And this is equal modulo C to A plus B. So if you look, A plus B fixes, A plus B. modulo commutativity. The thing is, with freshness, we lose this. With freshness approach, don't get this solution. If you do AB fix X is equal to X, using the standard approach with freshness, we are going to miss the solution X goes to A plus B. Okay, so because of that, I decided to change the approach of dealing with alpha equivalence in order to capture solutions like this. So, but how is the syntax? So we deal with nominal terms. They are like an extension of first order terms, but we have a construct for abstraction. So an atom is a term, and function application is a term, and abstraction of A in T is a term, and a suspension, a suspended variable, pi fixes pi x is a so this action, permutation action here is used to apply renamings of names. So how does this action works? So for instance, if you have, let's see this, the permutation action A, where the permutation is AB and the term is f of t, how does it act? So you basically, the permutation acts homomorphically on function symbols. So it's going to be f of the permutation AB on t. So if you have, for instance, abstraction of t of A in t, and you want to apply this permutation, so it's going to be abstraction of B, and then you pass the permutation homomorphically to the inside. It's AB acting on t. Okay, and when the permutation finds, for instance, a inside, it's going to swap A for B. So how do we equivalence via fixed point constraints? So we need some nomenclatures on terminology. So we are going to use this symbol here as alpha equivalent to T, this symbol with this symbol on top, just to mean that we are using we are going to use this fixed point constraint that I'm going to define below. So it means that S and T are alpha equivalent. And pi fixes T, this is how it's called, pi fixes T means that pi applied to T is equal to T modulo alpha equivalence, okay? And pi fixes X is a primitive fixed point constraint, and if you have a finite set of primitive fixed point constraints on variables, you call it a fixed point context. And another notion, support of a permutation. So the support of a permutation coincides with the domain. So it's a set of names A such that pi of A is different from A. So intuitively, a pi effect on T except for the renaming of variables. Okay, so if you write AB fixes this abstraction A on A, if you open, if you unfold the definition, you are going to have AB of abstraction AA is equal to abstraction AA. I'm just unfolding the definition here. And then abstraction AA is alpha equivalent to abstraction BB. Okay, so it fixes it has no effect on bound names. Okay, implement this. So this is the fixed point rule. So for instance, pi fixes f of T1 Tn under the assignments in upsilon if pi fixes each term T1 to Tn. And pi fixes A if pi of A is equal to A. Pi fixes an abstraction of A in T if, this is a bit more evolved, if pi fixes this AC1 acting on T, is a new name. Okay, so C1 and C2 are new names that do not occur anywhere in T or in upsilon. And for implementing alpha equivalence, we have all these rules. I'm not going to all through them, but an interesting one is Upsilon proves that abstraction of AS is equal to abstraction of BT if S is equal to AB applied to T, and AC1 fixes T when C1 and C2 are new names and fixes the variables of T. Okay, so nominal unification via fixed point constraints. So the idea is similar to the normal standard nominal unification. You have equality constraints, which are questions regarding equality between nominal terms. Of course, now we are dealing with alpha equivalence, but we also have questions regarding the permutations that fixes terms. Okay, so if you have a problem PR that has fixed point constraints and equality constraints, a solution would be a fixed point context and a substitution, such that this context phi proves that sigma for each fixed point constraint in the problem, and the phi makes the equalities hold for each equation in the problem. Okay, so as expected, we follow the standard. We define a set of rules, simplification rules, and then we apply these rules in the problem until we reach a point where we cannot apply any simplification rule. And then if there is a solution, we are going to have like a substitution and a context that satisfies the problems, the constraints in the problem. This was defined, the set of rules are these. It was, they were given in a previous FSCD paper. So they are basically they're very similar to the first order unification simplification rules, but we have now rules for abstraction. Okay, so basically we are applying the deduction rules bottom down. So I'm not going to spend a lot of time here, but for instance, if you have a problem, abstraction X is equal to abstraction of A in X is equal to abstraction of B in Y, we apply the rules and we get like a context and a substitution. About the nominal disunification. Now we have a unification problem, but we also have these equations. So we have like several number of these equations, and we want to find a way of solving the equations in PR and solving these equations. Okay, so how we are going to do this? So if you have this example, you want X to be equal to f of Y, but you don't want Y to be equal to A, nor Y to be equal to B. So you can map X to f of Y, but you need to be careful that your Y cannot be A or B. Okay, so this is what we are going to do. We are going to first solve the equations, and then we are going to deal with these equations by looking at the associated equations. So I'm going to see what I have to do for Y to be equal to A and Y to be equal to B, and I'm going to remove this from the big set of solutions, okay? So, so for that, we are going to define the pair with exceptions. So if you have a pair with exceptions, is like a context and a substitution minus a set, a family theta, which has this form, is a set of, it's a fixed point context and a substitution. And we are not going to detail, I'm not going to explain very well. This index is here, it doesn't matter, it's just a set of fixed point constraints. And basically, this theta is going to be the solutions of the equations that are associated to these equations. The theta are the solutions that I don't want, okay? These solutions would make these equations false, so I don't want them, I remove them. Those are the exceptions. So, so a solution to a disunification problem would be, so given a problem PR with several these equations, a solution nabla lambda, delta lambda would be a solution of PR. It satisfies every equation in PR, and it satisfies the disequational part, which is this set of these equations of P. What it means, to satisfy the disequational part, it cannot satisfy the equations associated, okay? So for us, a solution is going to satisfy the equations and not satisfy the equations associated So for that, we need to check if a pair with exceptions is consistent. What it means to be consistent, you need to have at least one instance. Okay, so there is at least one solution that satisfies the equation and not the disequations. If it happens, we call this pair with exceptions consistent. And for us, a complete representation of a problem is defined in terms of a pair with exceptions for this problem. And we say that S of pairs with exceptions for P is a complete representation of the constraint problem P if S satisfies the following conditions. Okay, for every pair with exceptions in S, we have this relation. This pair with exceptions is smaller than nabla lambda. So nabla lambda is an instance of a pair with exceptions, and nabla lambda solves P. And if nabla lambda solves P, then it's an instance of some pair with exceptions in S. And it has to be consistent for all the set S, okay? So we have this main theorem, which is called representation theorem. So if you have a problem P, which consists of an equational part PR and a disequational part D, we define this theta as the union of the solutions of all the equations associated to this equation. So basically for each disequation, I'm gonna look at the equation associated, I'm gonna solve the equation, and I'm gonna remove the set of solutions, okay? So the set S, which is phi sigma minus theta, which are solutions of the equations, such that phi sigma is a solution of the equational part, and theta is not an instance of phi sigma. This is to make the set consistent, okay? That is a complete representation of solutions, and this is the algorithm. So basically, when you have as input a problem a disunification problem that has equational part PR and a disequational part D, first you solve the PR. If there's a solution for the PR, then you solve the you solve the PR with the unify, and then you look at the associated equations in D, and then you take the theta, and then you check if phi sigma minus theta is consistent. If so, sigma minus theta, this pair with exceptions, is a solution, or else it's not consistent and you don't have a solution, okay? The algorithm is the same as the one for first order disunification. And this is a complete problem. For instance, if Daniele, you have this problem.
You have 2 minutes.
Okay, thanks. So I'm not gonna explain with all the details, I don't have time, but so if you have a problem of this form, x equals to ABY, and the disequation abstraction x is different of abstraction BY, you solve the equation and you get this substitution, and you solve the associated equation of this problem, and then you get this big set here, theta, and you need to check consistency. This is a big part of the algorithm that I omitted, is for checking consistency, and which is the case, I return the pair, and this example here has a solution, okay? The solution is phi sigma minus theta, this set is consistent. So I went a bit fast to this because for checking consistency, we need like to call another algorithm for checking a nominal matching problem, and we need to take care of all the new names that you generate, and these things are a bit technical. I'm not going to talk about them here, but basically, I presented a specification of the nominal disunification problem via fixed point constraints. A study of consistency of pair with exception via is needed. We need like some technicalities for checking consistency. I presented an algorithm for constructing a complete representation of solutions. And this is going to be interesting to investigate extension of the disunification problem, modular equational theories that involve some kind of permutation of arguments. Okay, so this is an ongoing work, and hopefully you'll be able to complete this in the next steps. So that's it, I'm ready. Thanks a lot.
Okay, thank you very much.
These are my references. These are the references. Yes, thank you, Mauricio.
Okay, thank you, Daniele.
Can I stop sharing? Can I stop sharing my...
Yes,
because I can't see anything. Okay, right. I'm going to stop sharing because I can't see anything. Okay.
Okay. I didn't see questions in the chat, but I have some questions.
Thank you.
Danielle, the first one is why you say that this algorithm is complete. There is a proof?
Yes, we have a proof.
Future work?
Yes. No, we have a proof. We just didn't show here, but we have a proof.
Yes, I didn't
it follows from the complete. It follows from the completeness of the unification algorithm, because basically you're solving a unification, and since unification for nominal is complete, and it's complete. Okay. Sorry.
Okay. There is a question from Temur Kustia. In the inference rules, new atoms are used as a meta-level concept.
Yes.
I am wondering what you bring it down to the object level by the new quantifier.
Yes, thank you for the question. Yes, thanks for the question. It simplifies. The first approach we had for the nominal unification via fixed point constraints, the one that we published in the Logical Methods in Computer Science last year, was using the new quantifier, because we didn't need to worry about the exactly new name that we were generating. When we are going to do unification, we would look at the names that were new, that were already in the problem. But we were asked about different approaches, and one was not using the new because it might be a bit difficult. So this work that we presented here, we used like we generated new names, but this gave us a lot of, because you might generate new names when solving equations, and then you generate new names when solving these equations, and somehow we need to connect these new names generated separately, and this gave us some work. So the idea for the future work...
Daniele, Temur Kustia question is crucial regarding the complexity of the algorithm.
Yeah. No, but it's not going to...
Taking it as part of the meta language, part of the logic or of the logic itself will have crucial implication in the complexity of the solutions. I think this question very interesting.
No, it's going to make it easier. If you look at the fixed, if you use the new quantifier, everything is much easier. We don't need to worry about the new names that are generated.
Right,
that's the short answer.
Easier don't means less complex from the computational point of view.
No, it's, I don't know. We can investigate this.
I think that is an...
Yes, thanks.
To investigate.
I think it's going to, I don't know. I don't know how to answer. I'm afraid of answering and saying that it's going to be easier and less complex, but I'm not sure. I need to investigate. Thanks.
Okay, I don't see more questions. Thank you very much again. Daniele, I have to move to the next backstage for the next talk, all right?
Okay, I'm also going to attend the next talk. So if anybody wants to go into discussion room with me, please, let's do it on the break, because I want to attend the next talk as well.
Okay, see you in 30 seconds.